Okay, two housekeeping things before we start. About 20 of you signed up for in Hawks already. Please make sure if you have not done that yet, do that. If you're having trouble, tell me after class or send me an email. We'll get that straightened out. I did see some of you signed up, have the temporary access to it. It's not going to last to the end of the semester. So do make sure to get the code as soon as you can so you'll be able to finish out the semester. Second thing, your test is Monday. I know it seems like insane. You are going to be allowed an index card, 4x6, 3x5, whatever size index card you can get. You can write whatever you want on it. It has to be handwritten, cannot be typed, stapled, stuck to it, whatever else. So a handwritten index card is fine. I'm going to give you a couple websites today that you're going to be using to do some of the calculations on it. You'll be able to use your cell phones for a calculator. Don't make me regret it. And we'll be able to continue that for the rest of the tests. Okay, so because I'm not going to sit there and make you do out standard deviation by hand, or even using a simple calculator to type it out to try to do it out is a pain. So I'm going to give you calculators online that'll do that for you. Because I'm going to go out on a limb and guess the vast majority of you are not going to become statistic majors that are going to have to do this all up by hand. So calculators and technology is the way to go with a lot of the stuff. So I'm going to allow you guys to use that as well. The websites will be linked on my website, so you'll have access to those. Yes.
If you have a calculator already,
yeah, you can use a calculator. I don't care. That makes no difference. Like I said, just some of the formulas are going to get kind of complicated, and there's a lot of steps, and it will take you a lot longer to do it out unless your calculator has the button that actually does it.
okay.
So,
Yeah.
All right. Any questions on those? All right. So we're going to go through chapter 3 and 4 today. Chapter 3 is going to be pretty quick. We'll do chapter 3, and then we'll take our break, and then we'll do chapter 4 after. Chapter 4 is a lot of the formulas and stuff like that. Some of it you've already seen before, and a lot of chapter 3 you've probably seen before too. So it won't be too bad. All right, first thing, a frequency distribution. So whenever we're looking at creating a chart or a graph, we need to somehow organize the data. So one of the easiest ways to do that is a frequency distribution. This one is used quite often when we're looking at qualitative data, not quantitative, qualitative. So this is data that does not necessarily does not have to be numerical, and we're not going to be able to do a lot of calculations and stuff with it. So you're literally just going to choose the classifications and count up how many is in each class. So it's quite straightforward and simple. You do not need to write everything that's on the board down. Because when I show you it, it's going to go, oh, okay, that's simple. These are frequency tables. This is literally what you would do. So you ask a question like, in general, how would you rate the quality of American public schools? And you count up how many people said each of the options. That's all a frequency distribution is. Okay? Nothing special, nothing crazy. That's all it is. So we've got this data. This was a survey that he did. Honestly, the book was written in like 2015 or 2016, so it's been a little while since this was done. They asked these questions, and they put the information down. So they've created a frequency distribution. It's easier this way than giving you a list of all the responses, all 1,250 responses. Like, you're just not going to go through and read that. That's why these tables are important. However, if you're math phobic and hate numbers, you're going to look at this and go, huh? So what do? Well, we create pictures. I'll go back to the other screen in a second. We create a bar chart. Okay? Bar charts are really easy for people to look at. It gives you a ton of information. Notice that this bar chart starts off at 0 and goes up. So there's no breaks in it and things like that. Right? A bar chart is a simple graphical display of a frequency. These are in percentages. You notice the first table I gave you was not in percentages. How did they get the percent? They just counted how many it was, divided it by the total number of it. So why is percentages better than just the raw numbers? Why would you rather a percent than the raw numbers? If I told you 462 people said it was excellent, Right. Like depending on this, how many, it's like, okay, now I got to give you another piece of information. I got to tell you how many people said it. And then you got to sit there and do the calculations. Okay, is that good, bad, what? It's like percentages helps standardize that numbers. We know it's basically out of 100. So when you say 37%, oh, that's less than half. That might not be as good as it sounds. That when we said 462 people, it's like, so percent's just, it's one of those things that we recognize and we understand what it means, and it helps us to bring our data to the general public. And the same thing with the bar chart. This bar chart wouldn't have changed if I had changed the numbers from 0 to say 500 on the bottom and listed the numbers up. The bar chart would have been exactly the same. And at that point, even if those numbers were down the bottom, if you looked at the bar chart, it's, oh, okay, you could recognize that, yes, this one's higher. It's like very serious is a lot higher than somewhat serious. That means a lot more people were looking at that than the other one. Everybody in here has seen a bar chart at some point in their life, right? Okay. All right, so here's another bar chart. So this is sales performance for Susan, William, Beth, and Rob. And the two bar charts below it both show the exact same data. Okay. If you were just looking at the bar charts, would they give you the same impression? No. All right. This bar chart on the left starts off at 0 and goes up to 250, and it shows down the standard thing. This bar chart starts at 180. So if you look at the one on the left, they're all pretty similar. They're not that far off. If you look at the one on the right, Susan's doing a lot worse than everybody else. Okay. So it's that type of situation where you look at bar charts, you can use it to manipulate opinion. Okay. It's like if I was HR and I wanted to get rid of Susan, I'm sharing this bar graph. Susan's the weakest performer. Yes, she is. She's not. She is the lowest performing salesperson, but she's not that far off from Beth. She's 20,000 off from Beth. But if I want to get rid of her, I'm sharing this one with management. And they're going to look at it and go, wow, Susan's way lower than everybody else. Okay. So this is a hypothetical situation, but you can start to see how you can use those graphs to manipulate opinion. So when you create a correct bar graph, you want to start off at 0. You want to have equally marked ranges in it, the breakdown, so that this way it shows the data accurately. All right, actually, before we get to the pie chart, we're going to get to the pie chart, don't worry. Now with the pie chart, I'll do something else with you guys afterwards. All right, so pie chart. Everybody seen pie charts before? Good. So what is the one? I've had administrators in the past that they fell in love with pie charts, and everything had to be a pie chart. A pie chart has a very specific use. A pie chart has to be in percentages and has to add up to 100. Okay. If it doesn't, it's not a pie chart. All right. So when you're using pie charts, that's something you have to think about. These two, this is the bar graph for it, and then that's the pie chart for it. So this is the federal government spending in 2015. Here, I'll make it a little bigger, because I'm going to show you today's in a minute. All right. So in 2015, the federal budget was $3.36 trillion. Okay. Social Security made up 38%. Medicare and health made up 28%. Defense made up 16%. The other programs were 12%, and the net interest is 6%. Okay. Medicare and health is, so that's basically all your health programs and Social Security. So those two are the government likes to call them entitlement programs. Those are the two programs that come out of your paycheck every month or every week. That's FICA and Medicare. Okay. So how much money did we spend on Social Security in 2015? How would you be able to figure that out?
Let's figure out 38% of 3.36 trillion.
Good. So find me my number.
Divided by the total?
Nope. You're just going to. So how do you actually? This is a very good question. How do you guys find a percent of something?
Do it, but they're basically-
Multiply. So you're going to multiply the total amount by 0.38.
No.
Yeah.
Okay.
So multiply 3.36 trillion by 0.38. That'll work. You could also multiply by 38 divided by 100. That'll give you the exact same answer too. Or hit 38 and then hit the percent key on your calculator. That'll also do it for you. But 3.36 times 0.38 will give you the percentage of that budget. So how much was Social Security in 2015? There's a reason I'm showing you this.
1.27.
1.27 trillion. Okay. All right. So that's Social Security. What's defense? Okay. So how much is that out of the entire budget? What was it, 0.5 something? So 0.53 billion? Or 530 billion would be the exact same thing. All right. So one of the things when we're looking at percents is percents are of something. Okay. So those are the percents of the 3.36 trillion. When we look at another year, the percents will change, but also the total changes. Okay. So when you're looking at charts like this, you have to keep that in mind. So this is last year's budget. Okay. And this budget was $6.3 trillion. So this was the budget 2023. It was $6.3 trillion. So almost double what the budget was in 2015. Okay. How much is Social Security now? It's a lower percentage, but is it a lower amount? That's the thing. So when you're looking at it, and that's where the percentages really matter, because when we're looking at percent, okay, the percent's gone down, but has the amount of money that's being paid into, like being paid out, gone down? Okay, so what's Social Security now? $1.3. All right, and last time it was 1.27. So the amount of Social Security really hasn't changed from 2015 to today or last year.
But really the relative amount matters more.
So the amount of the budget, so that's the thing. When we're starting talking about like the massive budgets and stuff for the economy, it's a matter of where everything's going. So our budget has almost doubled, but the amount of money coming out to go to Social Security really hasn't changed because the amount of people that are claiming it are still very similar. Okay, so in the last 9 years, we haven't had a massive influx of people retiring or getting to that age where they can start claiming Social Security. So that amount really hasn't changed. But that also goes into the fact that it hasn't really kept up with inflation, which is easier. So people who are on Social Security are on fixed incomes, and that runs into it too. All right, so we found defense before, right? Has the defense gone up? So the last one was 16%, right? So now we're down to 13% of our national budget. So what are we at? So 0.82 or what? Yeah. All right. So we're at almost $820 billion international in the defense budget. So the defense budget's gone up by about 300 billion. The other thing that's really important is to look at is this one. The interest on our debt. So in this one, it was 6% of 3.36 trillion. That one has gone up the percent. And the budget's gone up. 10% of all the money that our federal budget goes is to paying interest on the loans that we've taken out because of the deficit. That $35 trillion national deficit, that's what all that interest is covering that. That's going to keep going up. That's taking up a larger and larger portion of our budget every year, which means less money to spend on other things. Okay. So it's percentages are one thing when we start talking about, like, we're looking at things, percents are good because it can allow us to compare things and look at stuff. However, they also can be used to hide things too. Like, oh, because somebody can say, we've lowered our defense budget. We've lowered the defense. It's only 13% of our national debt budget now instead of 16%. That's a good thing. And some people look at it and say, yeah, that's great. But it's a 13%, it's 3% less of a much bigger pie. Okay. And then other people look at Social Security, it's like, oh, Social Security was 38% and now it's down to 21%. We're cutting Social Security. Not really. The numbers are staying the same. So you can start to see how pictures are great. It shows great information, but you got to dig a little deeper to see why are they showing you certain things? Why are they pointing out certain things? Okay. So just little things to keep in mind.
Also, the value of the money is different. The other one is adjusted.
Well, yes. But when you're talking in the trillions of dollars, it's not much danger there. There's also, so this one breaks out. This little blue one right here. This is the other category. Just to give you a general idea, education's 4%. So you know how those people are like, oh, we're spending all our money overseas. 1% of it goes to international funding. So if we were to cut all funding to going overseas for anything there, you'd save 1% of the federal budget.
Spread agriculture. So
That's basically your farm supplements and stuff. That's the money they're giving farmers for crops and stuff like that, and your oil resources and stuff. Again, it's believe it or not, it's very small parts. But when you're talking about trillions of dollars, that's still like $63 billion. Like that's still a lot of money, right? But it's pittance compared to the chunks that are up here. So, all right. Let's see. Okay, so we talked about those. There's a few other ones. Hold on a second. I see one other thing before I go into the other one. Oh, yeah, I did miss the stack ones. I knew I missed one graph that I wanted to show. One other bar graph that you'll see quite often is a stacked bar graph. And it would help if I showed the right graph. There we go. These were Winter Olympic medals. So bronze, silver, and gold. Whenever you're looking at, so our categories in this situation would be the countries. And then they stack the medals on top of each other. So this way it's easier to recognize where we're looking at it with. Instead of showing you a graph. So these two graphs show the exact same thing. but this one's a lot harder to read. Same graph, same information, except it's a lot busier. So it's a lot harder to read that information. So stack bar graphs really do help with that information. And it is one thing that you do see quite often, especially when you're looking at these things. Everything that we've talked about, except for the budget with the money, these are all qualitative type graphs. So bar charts and pie charts, you can do stuff with qualitative information. We could use them for quantitative, okay? But the rest of the graphs we're going to look at, you cannot use for qualitative. So these are the graphs that if you're going to do anything with qualitative data, you're going to be looking at a bar graph or a pie chart. All right. Let's look at quantitative information. All right, so we talked about at the beginning a frequency table where we're counting up a bunch of things. When we're looking at quantitative data, our frequency distributions become a little more complicated. Okay, because we're no longer looking at individual categories. We're going to be looking at ranges of data. So if we're looking at heart rates per minute of 50 students, so here's all our heart rates. And notice they're not in order. So when we're looking at trying to create a frequency distribution for it, we need to come up with ranges we're looking at first, and then we count the information in those ranges. There's very specific rules on how this is done. The next slide is going to have them all. I'm going to show you what you need to write down because it's not everything. Because there's a lot. So you're not going to have to write it all down. All right. So I'm going to make it a little bigger for you. Because there's no way you're seeing that. Yeah. All right, so first one. So the first thing you want to do is you want to figure out how many classes you want. So this is those ranges. So in this first one, the one we looked at here, we had 1, 2, 3, 4, 5 classes. And that's what you consider a class, is how many different breakdown you want to do of it. Okay. You don't want a million of them because it's going to mess up your data. It's going to make it too hard for you to understand what's going on. So they say 4s, you want more than 4. The last one we had was 5, but you also don't want 20 or 30 of them. Most of your classes are going to be between like 5 and 10. It really just depends on your data. Because again, you want to see what's going on with that data. The next thing, you want to determine your class width. So if your data has nice breakpoints, so if we're talking about years like the 60s, 70s, 80s, 90s, 2000s, those type of years, break down really nicely, you can do that. Not everything does. Like the heart rate ones did. So to do that, to determine where you're starting and where you're ending, your class width is you're going to take the range, which is your maximum value minus your minimum value, and divide it by how many classes. This way, each class is equal. That's really the biggest key with that one. You want each class width to be equal. So formula, definitely important to write down. Whenever you're dividing, you could get a decimal. Typically, you want to round them off to make your life a little bit easier. So yes, your classes won't necessarily be like a perfect thing. There might be a little extra at the beginning or a little extra at the end, but that's fine. You want to keep them the same width though. So when we looked at this one, I started off with my lowest number was 57. What's 57? 62 is the lowest. So, and then we also didn't have anything that goes up to 106 in here either. Okay, so they rounded them to get them a little bit easier, and noticed what did they do? They went from 57 to 66. They basically made each class 10. What's 57? What's 67 minus 57? No, the other. 66 minus 57. 9. But I said the class width was 10. Why? You count. 57, 58, 59, 60, 61, 62, 63, 64, 65, 66. Okay, so your class width is 10, not 9. Because all the numbers that are going to be in there are going to be between 50, well, including 57 to 66. Okay, does that make sense? Very important to think, because that's really, really easy to screw up when you're looking at them. Huh? So when you're looking at it, 66 minus 57 comes up with 9, because when you're subtracting them, that's what you get. However, when you're looking at the numbers that would go into it, you're counting the endpoints. So from 57 to 66, there's 10 numbers, because you're including the 57 in there. Or when you subtract it, you wouldn't, basically. Okay. So each of these is 10 long. And notice there's no overlap in them. This one ends at 66. This one starts at 67. So you're not trying to figure out, okay, which one's my value going to go into? All right. They have to have clean endpoints. All right. Do this one. All right. Your class limits. You have the lowest class limit, lower class limit, and the upper class limit. Those are your endpoints, like the 57 and the 66. As it says here, sometimes using a smaller number for your lower limit, it's okay. Like the last one, my lowest number was 62, but they chose 57. Same thing on the upper end. You can do that if you want to try to keep those ranges nice. Okay. So you don't have to choose the lowest number and the highest number when you're looking at your beginning and your endpoints. It's like the heart one, it was 57, but the lowest number here was 62. The upper one went up to 106, but the highest number here is not in the hundreds. I don't see any hundreds in there. It's like 93 or 98. Huh? Yeah. Yeah, because they wanted to keep these to 10. And then once you've come up with your classes, you count how many's in each one. Hold on, I'm trying to get a chart for you. They're not giving me a very nice looking one. Okay, this is good. All right, here's what you're gonna do. All right, here's all the temperatures from Norwich for June. I want you to make me a frequency chart, and you're going to have 5 classes. Okay. Using the daytime highs, not the nighttime. Using the big number on each one of them, not the little numbers underneath. I might be able to stretch it, but I don't know if I'm going to be able to.
Make one for the, daytime.
Yeah, just the daytime. And it's not giving me the bottom. Oh, there you go. Okay. Better? That's about as big as I can make it, unfortunately. And you want 5 classes. Remember the very first step. How many classes? I'm telling you that. Okay. Then you have to figure out the class width. That's that. So figure out your class width next. What's the lowest number and the highest number? Or where do you want to start and where do you want to end? That gives you your range. And then you divide that by how many classes. And there's multiple answers that are going to come up with, not necessarily one specific answer. So figure out where the lowest temperature is and where the highest temperature is.
And then what did you say to them?
And then figure out how much is between those, and then you're going to divide that by 5. And I'll tell you how many, what your class width is.
5 plus instead of
5 plus, yes.
isn't there? These are right. 30, so it should be. Supposed to be 6. Right? Nuts. Oh, I forgot that.
The lowest is a 72, the highest is highest is 93. Lowest is 63, the highest is 93.
I subtracted it, multiplied by 5, rounded up to 6.
It's actually 93. It's half and 30. But that's fine.
Yeah?
You did it without, yeah.
Why you start? Sets of 6, I wanted it from the last one, we were a little bit lower. Cause I didn't want to end up with like, the bottom one, like 180.
Work on starting that. You did 7.
Hold on, so the bottom and top ones
Yeah,
could be
60. Yeah,
lower or higher, but
I was like, I was trying to figure out, yeah, that's where you're,
yeah, because I mean.
Yeah. you're doing 5. 63, 64, 65, 66, 67. That's 5, not 6. It's, those are the little things.
the minimum maximum ones can be.
This
higher.
one is exactly the right, exactly what it is. Yeah. You do, no, if you subtract, it's always gonna be 1 less than your class weight. If you subtract the 68 minus 63, you get 5, but your class weight is 6.
Oh, okay.
Each part's the same one. Doesn't work. Should it? I mean, this class is bigger.
It doesn't work if you do 6 unless I'm doing the math wrong.
Because yeah, it would be 87, 92.
You're right.
So one of them must be bigger. Yeah, because the highest one is right, but if like each class is supposed to be the same size, but this class is.
Oh, yeah, because you're gonna be off.
Or down.
Yeah.
Like that.
Yeah.
Is that?
Yeah.
I'm supposed to.
Just make the last one 93.
Yeah, okay. But that.
Yeah, that one is 1 off. Yeah.
Because all the class stuff is the same size.
Yeah, so technically you could make them all 7. So this way you can go a little, that's where you can go a little lower, a little higher to make them all exactly the exact same.
Yeah, but so like when you make classes, you're like this top,
The highest and lowest ones.
Yeah,
lower,
you wanna make sure they're all
are
there.
the same size. Like the top and
So you
bottom.
did 5 degrees. Actually, you did 6. So actually what ended up happening was you did exactly what ended up making it all equal. You did 7 in your class, which is something. Because if you subtract it, you get 6. Remember, it's always 1 4. Your class was 1 4. You have to subtract, which is fine.
How does that tie in with the formula?
So when you get it, it comes out to be exact. It always is going to end up being, if you do exactly from those numbers, you'll be 1.
It's always the way.
Yeah, it'll be 1. So that's why if you go up by 1, so if you do 7 for your class width, you'll end up having the trust.
Lower a bunch of them.
When you're, if it came out to be a decimal, it wouldn't have mattered because it would have worked. If you round it up anyway. This is coming up to, oh, that's the one.
Because like, I did like 60.
So you're gonna do, so do 7.
Oh, do separate.
Yeah, because that's what's gonna happen, is if you're gonna put one off, you end up at 92.
Okay.
So we're gonna do 7.
Okay.
It's fine. You just did one. There's a check. So. Okay. Yes, but you did a little bit. The lowest number is 63 and the highest is 93. Oh, no, you have to choose the lowest and the highest. Otherwise, you get something like that, they're not. You're gonna misplace it. Every value has to have the bid to go into basically. Is the key piece. I didn't have that. I literally just pulled last month. So I'm looking at this. That's right. I'm hoping I haven't counted it yet. So. Yes. Yeah, always round down. This one. Always round down. Yeah, because if you round down, you're gonna lose data. Yeah, that's fine. Yeah, I don't know what the actual numbers are. I didn't count them. This happens to be literally last June of 2024 in Norwich. So the wonderful thing about that and the internet, I can just pull things up. So when you're looking at your, shrink this a little bit. So when we had the 93 minus 63, which gives me 30. And we divide by the 5 because I said 5 class lists, we got 6. What happened was we found out really quickly that we couldn't do 6 because 6 doesn't give me the right amount of spaces at the end. So you always have to go up by 1. And I'm almost sure it actually says that in there too.
But how did you figure that out?
Because so here's what happens. If you did 6, you get 63 to 68. 69 to 74, 75 to 80, 81 to 86, and 87 to 92. I have nowhere to put 93. So that was doing by 6. If it was ended up coming out to be like 5.5 or 5.6, you wouldn't have had that problem because you would have rounded up to the 6 and it would have been fine. Because it was exactly 6, that's where you have to go, okay, I have to go up by 1 to make sure I have enough bins for everything to fit into. Now your choice comes into, we know we're going to be over where we're going to be starting, right? I just need to make sure I have 63 and 93 in there. I don't have to start at 63 and I don't have to end at 93. So
They all have to be the same size.
they all have to be the same size, yeah. So we could do 62 to 68, 69 to 75, 76 to 82, 83 to 89, and 90 to 96. Okay, and now that's a width of 7 with 5 classes. Yes. No, that doesn't matter. Doesn't make a difference. You could have started a little lower, that a little higher. Like if you did this one to 61, that would have been 95. You did that one to 60, that would have been 94. Like you don't have to worry about trying to get it exact in there. The goal is just to be able to organize the data, because then what we're going to look at, and not in this one because I literally just filled this one out right now. Have that. Yeah, I'll go back for a second. I'll do a few other things first. We'll be able to graph this and get it in a second, which I'll show you in a minute. Yes. Do you have a question? Okay. All right. So if we look back at our heart rate, now that everybody has a general idea on how to find classes and stuff, there's two other things that we can do with once we get those numbers. We can find our relative frequency, which is just the percentages. Same way that we did before, you take how many was in each one divided by the total number. So in this case, we've got our relative frequency here. You'll see relative frequency listed as a percent sometimes and as a decimal sometimes. It means the same thing. How do we change a decimal to a percent? Yeah, remove the decimal 2 places. It's the same concept, right? And going backwards is the same thing. So 0.04 is 4%. So they mean the exact same thing, so don't freak out if they just leave it as decimals or change it to a percent. I don't have a preference. The other thing that we can do is we can add them all up. And that gives us what's known as our cumulative frequency. This is a great way to check your work and make sure that it comes out right. Is if you add them all up, it should come up to be the exact total at the end. So in this case, our cumulative frequency comes out to be 50 at the end, as it should, because we had 50 heart rates. The other nice thing is it allows us to actually look and say, okay, how many heart rates were below a certain amount? Because we have that number easily available there. This one's not used as often as the relative frequency is, but like I said, it is a nice way to check your work. And then they have the relative frequency the same way for cumulative, and it should come out to be 100% or 1 at the end, because that's the total. But like I said, the cumulative ones are a little less useful, and you won't see them as frequently. Yes, just adding them up. You're just adding back. So the first one's 2 because there's 2. The second one's 12 because it's 10 plus 2. Next one's 44 because it's 32 plus 10 plus 2. You're just adding as you go up. All right, this is the important one. A histogram. All right, so a histogram is a bar graph, very similar to a bar graph, except it's using a frequency chart that we just created to get. So what a histogram does is it allows us to organize the data and see patterns forming. Okay, so if you look at this, what kind of pattern do you see forming in it? What do you notice happening with the heart rates? Yeah, the middle seems to have the most, right? Okay, and the outer edges seem to have the least. Okay, what else do you notice about how this histogram was created? Okay. Starts off at 0. That's an important thing. It's good. All right. I'm going to, you look real quick. I'm going to go back and graph the chart for it. So this is the chart that made this.
Yeah, so it's like 0.5 and 7.
All right. So yeah, so it doesn't start off at 57 and go to 66. It starts at 56.5 and goes to 66.5. So the histogram, the difference between a histogram and a bar chart is a histogram is continuous. Okay. There is no break in it. So I can't do 57 to 66 and then 67 to 76 because then I would have a break.
So there's no breaks in history.
There's no breaks in histogram. That's why there's no, if you look at the bar charts, there was gaps between the bars. Notice the histogram, there is no gap. Okay. Because they go right up to each other. So we can't put 66 and then 67 in between that first thing. And we can't stop at 66 because then is the 66 number in the first bar or the second bar? Okay. So we have to go halfway between the values that we have. That's where the 66.5 comes into play. So it's always halfway between the two the two endpoints. So between 66 and 67 is 66.5. So that's the break point. And 66.5 doesn't exist in our values. So we know that wouldn't be a value that I would have to guess which one it's going to be in. Does that make sense?
So all histogram charts will have that.
We'll all be at decimals at some point, yeah. Yes, unless your numbers are all in like tens and something like that, and then you could technically use like 15 because you don't have 15. But almost all of them end up being a decimal because you have whole numbers. And if you had decimals in your values there, you might have to go out an extra decimal. It might have to be 66.05 or whatever else, depending on what the values and stuff are. But those values there should not be the endpoints in your class widths. That makes sense? That's the big difference between that and a bar chart. A bar chart would have literally just said right below it, 57 to 66, 67 to 76. That would have been a bar chart. That's how you would have done the bar chart. And there would have been a little gap between them, and that would have been fine. But the histogram has got to be continuous. Let's see if I can find. Actually, we're going to go back to our numbers here. Did everybody write the numbers down? Temperatures.
I wrote them down there.
All right, hold on. I'm going to move this up. Because I want you to actually make me a histogram for it. We're going to look at it. Yeah, that's fine. Huh? Yeah, do it with the sevens. I'm doing it too, so give me a minute. Because I have to count them up too. My horrible drawing skills. Yeah. So you're gonna use, so you'll start off at 61. If you use these, you'll start off at 61.5. And your last bar will be 96.5. No, so you're going in between them. So it'll be 61.5 and 68.5, because that's between those two.
Go to 400 temperature. So do the bar graph.
Well, so count the first.
Oh, how many like if there was?
How many do you need to get? Yeah,
Oh,
yeah, you need to have the count first.
just for it.
Go to the back. That looks good. That's actually right. That's exactly what I had. So hey, that means I kind of hurt. Okay. It's halfway between those two. Correct. Yep, exactly. What I did is I literally just made lots of little tally marks as I was going through the dates. I wasn't trying to look for each one individual. I was being forever.
I don't know.
So you did this. So 60.5. No, you want 59.5. You want before.
Okay.
And 60. So then the 66.5 takes care of both of them. You don't have to do this after, it's between them. So just make a little tick marks. As you're about to throw. That's what I got. So. So the count, that's gonna be your count. Yeah, like how many you had before. Okay, so you've done that. You need to get them into groups. So how many between six, so these are your groups. So how many between 63 and 69? That's gonna be your bars.
Okay.
You're fine. 62.5. I'll go along. The half one. Yes, that's what I got. No, you're fine. No, 66.5.
Okay.
Will
So
be the
I
next one.
just.
And you don't have to do the 67
Oh,
because
okay.
the 66.5 is a little above that one and a little below the next one. So your next one's going to be 73.5. Because it's between the two. Yeah, or a histogram. Actually. Okay, so first thing, you have your classes. You have the classes.
I'm not sure why you have that, if we're supposed to use that or
Yes, we're using those numbers.
make one of these.
Yes, yes. So the first thing we need to do is we need to figure out how big our class is. We determined before that it was going to be 7. Yes. Those numbers. Okay, so your first one's going to, so you're going to use these numbers right here.
Yeah.
Those are the ones. So the next thing you have to do is just count. How many of those are in each one of those? So how many numbers are between 62 and 68? No. How many actual temperatures up there?
Oh, okay.
Okay, so my suggestion to you, what I would do is I would start at the first one and do 79, and I would just only take marks next to those.
Okay.
So you don't have to keep jumping around and trying to find how many is the next.
Okay.
So get that, and then we can move to the bar. Oh, okay, you just got the last one. All right. we've got. All right. So you need, so we were doing 7. So our class was 7. Because that was the way, that was able to get us up to the 93 if we needed to. So you're gonna start at 61, that's fine. So you're gonna go 61 to 67. Yeah, 67. Right, so 67, and then that'll be 68 to 75. Yeah. And then count how many temperatures are in each of those ranges. Your first one, which your first class. Your first class is 63, so that would be 61.2 or 62.5, sorry. Because if your first one 65, 63, your first number is going to be 62.5. Then your next number will be. So somewhere, where's your classes written down? You need those. Where did you keep track of how many you were counting? Okay. Okay. So the first thing is we need to get our classes correct. So we're starting off. We were doing. I would start off at 62. So that's what I did on mine. So right on 62, and wherever our class was a 7. So it would be 62 to 58. So we your first class. And then start. So that's all these 59 do. And remember, you're basically adding 6 without leaving the class with a 7.
Yeah,
So
between 69 and 65.
that's it. Because if you had 7, you're actually having class with an 8. That's the easy, really easy to make a mistake. So add 6. So 75. This is 9 and 75. Okay, 76. Right. Once you get up to when you're past 93, then you count how many is each one, and then we can make our mark. That looks pretty close to what I asked. Pretty close to what I have.
Can you look at mine real quick?
Yeah, sure. We'll just say that. Okay. Your bars are fine. Your things down the bottom are not. You did a bar chart. If your first one's 62, that should be 61.5. And then this will be 68.5. That.
The last one's gonna be 96.5, 95.
Did you go up to 96 or 95?
96.
It'll be 96.5. All right, so this is what I did when I counted them up. So 62. If you didn't do the same classes as I have, you might be a little off on your numbers.
Wait, there's 30 total.
Yeah. 1, 5, 2 is 8. 8 plus 8 is 16. 16 plus 14 is 30. I have them all. I went back and checked that a couple of times to make sure I didn't miss any because it's really easy to miss things when I was looking at multiple screens. So I had 1 in the first one, 8 in the second one, 14, 5, and then 2. So that's the first step. Once you get your classes, do your counting. Then when we get our counts, then we can make our chart. Notice the middles. So I was starting originally at 62. So my first one is 61.5. And then I go to 68.5. You can see my horrible drawing skills. And then 75.5, 82.5, 89.5, 96.5. And I just counted by 5s because I didn't feel like writing 14 numbers. So 5, 10, 15. So that's 1, 8, 14, 5, and 2. Okay. And this is a nice, goes up to the middle, down from the middle. It was a nice curve. Okay. So these two graphs that we looked at, this one and the heart rate one, would be considered symmetric. What symmetry mean? Both sides are the same. So the left and the right side of the graph look the same. Okay, so that would be considered symmetric. No, it's not exact, but it's close. We have two other types of diagrams that you can see. You could have skewed right and skewed left. Does anybody want to tell me, looking at the bottom ones, why that could be confusing? Huh?
Right is on the left side.
Well, right. You're not looking where the bulge is. You're looking where what's pulling it is. Okay? So skewed right means this tail is pulling the information this way. And when we look in chapter 4 and we start talking about mean, mode, median, stuff like that, you'll understand. This will like really like crystal clear in your mind. So skewed right means that the tail is to the right. Skewed left means that the tail is to the left. Okay. So it is opposite, because everybody always looks at where the bulge is and goes, oh, that's no, it's where the tail is.
So the right's a positive skew.
Yes.
So it's positive.
Yeah. And not necessarily positivism good. It's because when we're looking at, and when we're going to the next chapter, we're going to look at standard deviation. The left side's negative, the right side's positive in terms of standard deviation. So that's why it's positive and negative. All right. One more type of graph we're going to look at. Stem and leaf plot. Has anybody ever heard of a stem and leaf plot? All right, this is a stem and leaf plot. So a stem and leaf plot takes the data and breaks it into groups of 10, or you could technically do 100, but most of them are in groups of 10. Okay. So 97, your stem is 9, your leaf is 7. So if you think about like we were just looking at with the temperatures, it's basically taking the 10s column and the 1s column and splitting it apart. Okay. It's just another way to make classes. The nice thing is what it does is it kind of takes that tally mark concept that I did and counting all one shot. Because you literally have your stems, 9, 10, 11, and then you just place the numbers right next to it. The proper stem and leaf plot at the end, they should be in numerical order. So after you write them down, you rewrite them in order. So this would be 97, 99, 108, 110, and 111. We now have a histogram. It's another way to write, it's another way to show your data. Yes. Yeah. Yep. Your stems would be 6, 7, 8, and 9. And then you'd have the numbers next to them. So it's just another way to show that data. Yeah, you're looking for the highest and lowest in the tens, basically. So here's Barry Bonds and Babe Ruth. Anybody like completely don't know anything about baseball? Please tell me you guys know who Barry Bonds and Babe Ruth is. No, I had a class last year that had no clue. Like the whole class, like had no clue about sports. It was like, huh? All right. So Barry Bonds and Babe Ruth. This was a stem and leaf plot showing their data. So this is their home runs in every year that they played. Okay. Babe Ruth did not have very many home runs in his first few years because he was a pitcher. And like Shohei Ohtani. But Shohei hits a lot more home runs than Babe Ruth did when he was pitching. So this is the stem and leaf plot showing Babe Ruth and Barry Bonds. We can look. So Ruth had 0 home runs, 4 home runs, 3 home runs, 2 home runs, 6 home runs, 11 home runs, 29, 25, 22. So you can see the breakdown in each one. Same thing on Bonds. Bond had 5, 16, 19, 25, 24, 25. Does everybody see how I'm getting those numbers? The number in the middle is the 10s. The number on the edges, the 1s. Okay? So that's 73. That's 54. That's 59. That's 54. Okay? But, huh?
So confusing.
It is. It's especially when you're looking at ones that have 2 sides. Like if I just eliminated this whole side, it's really simple. 46, 42, 40, 49.
So that's not the season.
Nope. That's not the season. That's how many home runs they hit in a season. So it's not the year they did it. It's just how many home runs they hit.
Oh, it sounds like it's more than one.
It is.
So the
It's
0, 1, 2, 3,
Their
4.
entire career. So Barry Bonds was from 1986 to 2007. Babe Ruth was 1914 to 1935. So it's their whole career. How many home runs they hit each season during their career.
But the numbers themselves divided into classes.
Yeah, those are the classes. It's 0 through 7 because the highest one was 73 and the lowest one was 0.
So it's stems what's in the middle.
The stem is in the middle. Yep. So what this does is we're asking, why do we have these? If you look at it, we can compare the 2 players. If you ignore the numbers and just put boxes around them, you now have bar charts. Or in essence, a histogram. So you can see this year right here, the 73, was way out of line with what he had been hitting all along. Okay, where Babe Ruth was, he had some low ones, but then he was pretty consistent in his years. Okay, so this, if we look at this as a nice little chart, this one would be skewed to the right because that's pulling it to the right, where this one is a little more symmetric. Yes, there's a bump down the bottom, but it's a little more symmetrical. Okay, so that's where your stem and leaf plots come in, is it gives you a way to organize those numbers pretty quickly. Okay, are you going to do it very often? Probably not, which is why there's not a ton of those on the test.
So are we gonna have to make the charts on the test?
The stem leaf plot only works if you're doing each class is like
Tons.
10.
Yeah, or you could technically do hundreds and stuff too, depending on how they break down.
Can't be like 7.
But the leaf should only be one number.
Yeah.
Whatever you're looking at, the leaf can only be one number. So, all right, the last graph we're going to look at, and then I'm going to give you guys your break. These graphs have become a lot more popular recently.
Colors.
Yes. And because it's one of those graphs that Well, yes, it's horrible if you're colorblind. I actually should have asked that. Is anybody in here actually is colorblind? Because if I switch colors, I want to make sure I know that. Okay, good. I don't have to worry about that. These are known as geospatial graphs. They are used a lot when you're looking at geography and looking at comparing information about different counties and stuff like that across the United States, and you're looking for patterns. So this is obesity rates across it, but you can see this. The most popular one was in 2020 when they showed. Actually, I'll pull it up and I'll show you. The most popular one is the actual election graph, which is kind of funny. Yeah. Oh, they don't have it all in there. Bad graph. That's the one I want. So this is the that's the election graph for 2020. Who won the election?
Red.
No, not
Oh,
really.
no.
Biden won it. Couldn't tell that by that graph.
No.
That's actually so. This graph is looking at the counties. The thing about it is when you think about in terms of counties in the United States, that was not what I wanted to do. Bad Wikipedia. The graph is accurate, even though it's on Wikipedia. The vast majority of our population, West Coast, East Coast.
Yep.
That's where the vast majority of our population. Okay. So out here, there's like nobody. Wyoming has the least dense population in the entire country. There's only like 700,000 people that live in the entire state. It's like maybe 1 or 2 people per square mile in Wyoming. Very pretty state, just nobody's there. So these are the types of graphs, and I guarantee you're going to see one come November. Same concept. But these are the types of graphs that when people look at it, you could start to see people coming up with those conspiracies. Like, wait, hold on. Trump had to win. This whole graph is basically red. It's like, but when you start to look down at where the population centers are, where the electoral votes are coming from, they're coming from the more popular states. And in those states, the most populous areas are a lot more Democrat than they are Republican. Your rural states are more the Republican states, and those are the red ones. So that's where we get this dichotomy. But that's another place where you look at these types of graphs and you can start to see how things change. Let's see if I have, let's see.
Yeah, there's so many like giant counties out west.
Oh yeah,
And
they're
it's
massive.
all-
Yeah. Like here's income rates. Oh, that's percent change. So this is how much people's income changed. That's not what I wanted. It's still changed. I want the whole graph. But you can start to see how these types of graphs can be very useful to start being able to look at patterns and where things are changing and whatnot.
They're changing both positive and negative.
Yeah, so because people lost money. So this is the personal income, like how much money people made compared to like where they lost. So if it was going down, that means they lost, like people lost, the actual income rate dropped in those counties. So, but the biggest change that happened after 2020 is in 2020, 2021, a lot of people moved out of urban centers into more suburban areas because of remote work. So you had a lot of people leaving California and Silicon Valley and moving to Montana, Idaho, those places, because on their salaries that were Silicon Valley salaries, $200,000, $300,000, they could buy a 1,000-acre farm in cash and not have to worry about rent anymore. So like you had an influx of those people leaving those areas. So that's why you're seeing that big change there. But those are the types of things you can start looking at when you look at graphs like this. Like, why did that happen? Like, we've got this data, we have this information, what changed into it? So we can start looking at those questions. Right. So, all right, go take your break. We're going to do a lot of calculations next in the second half of this class. No more graphs, but a lot of calculations. I have no control over it. One day you're going to come in and it's going to be hot in here. We're not going to complain. I've been in these rooms where it was like the AC wasn't working and it was so hot.
Yeah, usually the hundred is outside the colder, but some other-
Yeah.
7:15 again?
Yeah, 7:15. Yeah.
Is it that we can do it online or we have to?
It's going to be here. That's just a review. So if you want to do that, if you do that, the test's going to be almost the same type of thing.
Okay.
So it gives you a nice review on what the test is going to be. I was going to mention that at the end of class.
Tony,
Yes.
is this the right one? I wouldn't pick it up today. I'll be-
It looks like the right one, but hold on.
She said she had two different ones. She said if it wasn't the right one, I'd bring it back.
Yeah, that one's fine.
All that should work.
Yeah, that'll work fine.
Thank you.
No problem.
Do the 10:30.
All right. Everybody's back. On to chapter 4. First few things we're going to talk about still you probably have seen before. Then we'll get into some stuff that you probably haven't seen before. Mean, mode, and median. Have we heard of it before? What's another name for mean? Average, yes. So how do we find the average or the mean? Good. So find me the mean of this data. Huh? Add them all up and divide by how many you have. So when you're looking for average or mean, all you're doing is just adding all the numbers up and dividing by it. So 4, 10, 7, and 15 is what? 9. You can add them up. 36 divided by 4 is 9. Good. Yeah, there's a few more steps to it. Find me the average of those.
That's 120.
Yes. What was it? I should just do it. 32 or 31.8.
Yeah.
So that's the mean. And my mean of the original numbers was 9. So one of the things about mean is it is subjected to outliers. So numbers that are either really, really big or really, really small can change the mean. Okay. This is why a lot of times especially when you're looking at data related to people and stuff like that, you don't typically use mean or average, you use median. Okay. So just keep that in mind. We'll talk a little bit more about that in a few minutes. All right. Next one. You guys know how to figure out your GPA? All right. So your GPA, or even your class grades, in almost every class you've ever been in, is known as a weighted average. Okay? So a weighted average means that not everything is equally calculated. All right? So this is a weighted average. So you have your grades. Your grades would translate into a score or a GPA for it. So a B is a 3, an A is a 4, a C is a 2. Okay, so that would be the GPA associated with those. And if it's a plus or minus, it changes it slightly from there. However, in college, all your classes are not equally weighted. They're based on how many credit hours you have. So to find a weighted average, you have to find, basically, you're going to add up this 3 times. Easier way to do it is to multiply. So you're going to take this and you're going to get 9 because it's 3 times 3. So that class is worth 9 points. Your probability in stats class, luckily this one is only 3 credits, not 4, but this one's 16. Anatomy or 1 is 5 credits, so this is worth 10 points. And your English is 3 points, so that's worth 12 points. Then we add up those numbers. So 25, 35, 47. Now, we're not dividing by 4. You're dividing by how many credits you had. So you're dividing by 15. Okay? Because even though we multiply to get them, you in essence, to get that 9, you had 3 3s. And then you had 4 4s. And then you had 5 2s. So you're adding up how many of those you had, which would have been 15 of them. Okay, that's where the weighted average comes in. Problem is a lot of people will do this and then divide by 4 and try to figure out why that doesn't make sense. So 47 divided by 15 is 3 point something.
3.1.
Okay, there you go, 3.13. So your GPA is a 3.13. Okay. So that anatomy class pulled down your average quite a bit because it was worth 5 credits. So that's how you figure out a weighted average. You would do the exact same to figure out your grade in a class. You'd multiply it by whatever the percentage is and then divide by the score at the end. So, all right. Any questions with average? Think we're all pretty good with average? Good. It's known as mean. You're never going to see the word average anywhere in any of these books. It's always going to be called mean. Just keep that in mind. All right. Median. All right. How do we find median? Okay. So we're going to put them all in order and then figure out the middle one. So median is the middle number. All right. So the key to this, and which some people are going to forget at some point, you have to put them in order, which is the annoying part because sometimes that could be a pain. But if they're not in order, you're not going to get the middle number. So let's see, we got 1, 2, oh, it's just 2 1s, 2 2s. And I probably shouldn't be marking them off because that's going to screw you guys up. So we have 11 numbers. So you could do this a bunch of different ways. You can sit there and just cross off either one until you get to the middle. However, that works really well when you have a small amount of numbers. When you have a lot of numbers, that can become kind of tricky. The proper way to do it is to actually take how many numbers you have and divide it by 2. So we have 11 here. Divided by 2 is 5.5. So we're going to count over 5 from the one side and 5 from the other side. Oh, I missed one. Hold on. And the one in the middle is my answer.
Where did you get the 2 from? You always
Yeah, because you're basically looking for the middle. So that's why you divide by 2, because we're cutting the data in half. The problem comes in is when we have an equal amount of numbers. So in this case, we have 10 numbers. Let's put them in order. 72. So if we do 10 divided by 2, we get 5. Okay. So you count over 1, 2, 3, 4, 5. 1, 2, 3. I screwed that up again, didn't I? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this time we don't have a number in the middle. So you take both numbers in the middle. And you find the average of those two, the mean of those two, yes. So you add up those two numbers, so 85 plus 83, and divide by 2. In this case, my mean is going to be 84. Anytime you have an even number of values, yeah. You're going to add the two numbers together and divide by 2. Anytime you have an even number, that's going to happen. So let's say I added a score of 0 to this. Okay. If I added a 0 score to this, we'd now have 11 of them, right? So my middle number is going to end up being 83. Okay. 0 would be considered an outlier in this case because it's way below where the rest of the test scores were, correct? Just like the 123 was from my mean. Notice the median doesn't change by much. Okay. So median is known as resistant to an outlier. So because the outliers don't really affect it too much. So if you're talking about, you'll hear this a lot when you're looking at like incomes for states or housing prices and stuff like that. They will talk about the median house price or the median salary or the median income. You won't hear the mean because the median gives you a better representation of it. For example, the state of Connecticut is a perfect example of this. For a while, we were the wealthiest state in the entire country. We had more, our income level in the state of Connecticut was higher than anywhere else in the country. And actually, in certain parts of Litchfield, or not Litchfield, Fairfield County, like the Greenwich area, that was the wealthiest area in the entire country. More than Silicon Valley, more than anything else. Believe it or not, it's now in New Jersey. It's still not out in California, Beverly Hills, everything. It's still over here.
Okay, so I'm like,
The actual income for those people. Got to realize those areas, it's all the finance people from New York live in those areas. So yes, you have your rich engineers and stuff like that out in California and whatnot, but in those areas, you have all the wealthy bankers that come from Wall Street live in those areas. Now, I would be willing to bet the vast majority of you in here would not believe that Connecticut is the wealthiest place in the country, because we don't see that. That's where the median comes in. We have, actually, Connecticut has the most billionaires in the entire country. And one year, one of the billionaires' women died and balanced our budget with the estate tax. Literally balanced our budget for the year. Okay? So, like, that's how much wealth is in that area. It's like, you hate to think about that, but that literally actually happened. It was hilarious. I'm like, you got to be kidding me. Like, some people in government are just hoping for things like that to happen because it takes care of all their problems for a year. But we have such that those are the outliers. When you look at the state, like that outlier is this insane amounts of money would pull the average way, way up. And it wouldn't really make sense for what we really are. Like the rest of the state actually is very normal, like not really that wealthy. Hartford's another situation. It's kind of funny. So in Hartford, you would not consider Hartford a very wealthy area. However, we have multi-million-dollar homes in Hartford. If you've ever been up in Hartford by Elizabeth Park, where the governor's mansion are, those houses are upwards of $2 to $5 million a piece. If you go 3 blocks over, you're in the north end of Hartford, which everybody's heard about, and the average house price is about $80,000. Okay, so again, that's where those outliers can really pull in one direction and change it when you look at the mean. So that's why we typically use median a lot in those situations where outliers would occur. Okay, so that's where median really comes into play. All right. The last of the 3. Mode. What is mode? Yes, mode is the most common. So what's the mode of this one? Mode is 0.
so there no mode if there's.
What's the mode now?
No mode, or there's two.
There's two of them. It's bimodal. There's two modes. So this now mode has a 0 and 1. Unlike mean and median, modes can have multiple ones. Okay, in this case, I have two modes. You actually, if I had the 3, I can have 3 modes. That's fine. There's 2 situations where you will not have a mode. One where everything, so actually it's really one situation because it matters. When every number appears the exact same number of times. Typically it happens that they all appear once. But if they all appear twice, you still have no mode. Okay? If every number appeared twice except for one of them that appeared once, you have every one of those is mode except for the one. So if they all appear the exact same number of times, there is no mode. All right. So you could have no mode, you could have one mode, you could have multiple modes. That is possible. Unlike mean and median, where there's only one exact number. I want to show this first. All right. So we're going to go back to that wonderful definition thing that we talked about last class. I didn't talk about trimmed mean, but you can ignore that one. So, remember we were talking last class about qualitative and quantitative? Okay. Those have meaning when you're looking at mean, median, and mode because certain ones of them can appear and not work for other ones. So mode is the only one that you can always have a mode. Okay. So like I can look around and go, the mode of this classroom is gray because there's more gray t-shirts than any other color. Okay. That's possible because I'm not doing any calculations with a mode. All right. So you can do that. If I can put things in order, I can find a median of it. Okay. So ordinal, you can do median of too. However, to find mean, I can only do that if I can do calculations on it. And that's where that interval and net ratio comes into play. Because I can't do a calculation on the colors of your shirts, or I can't do a calculation on the rating you give a TV show. Can't add them up and divide by how many, it wouldn't make sense. So in that situation, the mean doesn't matter. The mode and median does. See people writing, so I'll leave that up there for a second more.
Initial question, did
Yeah.
you say earlier that you can find the mean from the median?
No. I don't think I did. So trim mean is just, you can eliminate the outlier and find the mean of what's left over. That's all a trim mean is. We're going to get to that. There's an actual calculation for that. Not yet, though. All right. Oh, I cut off the mode. Mode. All right. This is the bell curve. Learn it, love it. You're going to see it a ton from this point forward. Yeah, you're going to see this a lot. It's a quick class. However, I do know for a fact that if you go on Amazon, they have little sticky notes with the bell curve on them. And as crazy as it sounds, they can be very helpful because it's a pain to draw the bell curve constantly. And it's really easy to visualize it if you can draw on it. So if you want to go on Amazon and grab them, they're little sticky notes with bell curves. It's bell curve sticky notes or bell-shaped sticky notes, and you can find them. My last class, somebody found them, and it's like, oh, that works out really well, because then you can just take it and stick it in your notebook and write your stuff down. If you're using a tablet, just copy and paste it. That's basically what I'm going to do. All right, so this is a bell curve. If you remember, we were talking about before, we were talking about symmetry. A bell curve is symmetric. Both sides are exactly the same. Your mean, mode, and median will be exactly in the middle. Okay? So if we think about this for a second, if I added up all the numbers on this side and all the numbers on this side, and I divided it by how many I had, the mean would be right in the middle. It's going to be, because they're equal on both sides. Median. This half and that half are the exact same. So the median is going to fall right in the middle. If you notice the peaks in the middle, that number appears most often. So that's going to be your mode. So a bell curve, your mean, median, and mode are all right in the middle. So when we're starting to talk about standard deviation and those type of things, we're going to use mean a lot. But as a bell curve, that's always going to be the number in the middle anyway. So it's the same as your median and mode. Okay. The trick or the crazy thing comes in is when we start talking about those skewed things that we were looking at before. And this is where why it occurs and why we call it what we did. So remember, this was right and this was left. So notice where the mean is. Okay. So your mean is being pulled to the left because your outliers are down here, pulling it lower. That's why it's left. Okay. Because it's being, that mean is being pulled to the left by those outliers. This one, your mean is being pulled to the right by those outliers. Okay, that's why it's called right skewed and left skewed, or positive skewed and negatively skewed, because it's being pulled, the mean is being pulled from the center. And that's all because of those outliers that would occur there.
So I did write the number you gave.
Yeah. Yeah. Nope, I want. Just looking for a table to make you guys do the calculations real quick. All right. Find me the mean, median, and mode of those 20 numbers. You're looking at the units, not the days. All right, so what do we get? So what was the mean? 99 point. I'm hearing like 6 different numbers. and I didn't do it out, so
There are 5 modes. Yeah.
all right, that one's the easiest one to figure out. We'll do that one in a minute. What was the mean? So the consensus of the mean was right around 99, 99.9. All right. What was the median? 100. Oh, 105.5. And mode, we've got so 20. All right, that looks right to me. I don't know. I didn't calculate it out. What was the middle two numbers? Because there's 20 of them. 105 and 106. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. 9. I missed what? Oh. So 9, 10. So yeah, it'd be 101, 105, and 106. All right. So yes, 105.5. All right. Which of those is a better representation of the data? Should we use median or mean to determine this person's productivity? Why?
The middle number.
Okay.
Because those 20.
So which one better represents what this employee typically does? The median or the mean? Right, the median does, because we had those 2 days that was at 20, right? And are those typical of what he typically does? Or she does? No. Right, they're normally around the 100. So the mean has been influenced by those 2 days that they went home early sick. Okay? Good. All right. Two. All right. So here are 2 basketball teams. And I was nice, I put them in order for you. So those are the points scored for each team. Okay? So this is A, and this is B. Find me the mean and median for each team. Actually, I lied. These are a player. This is a player with 5 games. They played. Those are 2 different players. So this is going to make much more sense in the end. So find me the mean and median for each player. Makes much more sense than the next question I'm going to ask you. What'd you get? Okay. You're going to the Olympics. Which player are you taking with you? Why? Okay, so now we have a question. I'm going to hit on. I apologize. I'm going to turn on those lights. Well, close your eyes. I'm not sure which one's which. That's right. All right, good. So media work really, really well for certain things. However, there are situations where they could come out to be exactly the same. So we need to have some other way to be able to describe data and to get some information from it. So when I asked you which one of these players you want to bring, you guys said A because they're more consistent. So we have calculations for consistency. They're known as deviations. So the first thing we're going to look at that's going to help us is the range. So range is simple. Range is literally just the difference between the biggest and the smallest data points. Okay? The bigger the range, the more the variation. So if we look at this one, my range for the first one was 10. And the second one was 28. It's 20 minus 10 and 30 minus 2. Okay? So you're just subtracting the largest and the smallest. That'll give you your range. So that's one way for us to look at and figure out how varied the information is. The big one, the one that we're going to use pretty much all of the time, is known as standard deviation and variance. I'm going to show you the formula, and you're never going to use it.
So the range is the difference between
The largest and the smallest. So this is the formula for variance. If you're going to go on to stats 2, I know what these symbols mean. If you're not going past here, you're never going to see these symbols. You're never going to see this formula again. All right. I'm going to explain to you what this means. If you want to tune this out, you're more than welcome to. But some of the symbols actually are important. You're going to see these symbols, so don't totally tune me out. So variance is going to tell you how much things vary. So when we're looking at variance, we want to figure out how much each term varies from the mean. So this symbol right here, that U symbol, that stands for your mean. Okay, and this is for population, and this is for sample. So we're going to do both. So that symbol means the mean of the population. Okay. That little O symbol, that's standard deviation for your population. For a sample, the X with the bar over it, that's your mean. And S is standard deviation. So the big thing that you're going to have to know when you're going to use the calculator I'm going to show you is you need to know if you're dealing with a population or a sample. What's the difference? Let's see if you remember back 2 days.
People just like a group of people.
Yes. The population's the entire thing. Okay, so quite often you're only going to be dealing with the sample. Okay, in most situations you're going to be dealing with samples. Okay, but if it tells you it's population, you're going to use the population information. All right. So those are the symbols you're going to need to know because those are the symbols you're going to see in problems. You are not going to have to use this formula. That little e in the front means summation. You're adding up a bunch of values. That's why I said this thing becomes extremely complicated and long if you're going to do this out by hand. Actually, I can show you. So these are all the calculations that you have to do to figure this out if you only have 6 numbers.
But what are the names?
I'll go back 1 second. So this is just 6 numbers. Deviation, squaring it, and then having to add them all up and then divide. So these are all the different steps that they had to do for 6 numbers. Now imagine if you had to do 50 or 100. Okay, right. Not going to happen. There you go.
Yes, population variance.
So we're going to use, and I will put this up on my website. You can technically use any calculator you want online. If you search standard deviation calculator on Google, there's a bunch of them that come up. This just happens to be the first one and it works really well. So I use calculator.net. And let's see, 5, 10, 9, 11, 9, and 7. So all you do is you put the numbers down here. 5, 10, 9, 11, 9, 7. And hit calculate. And it gives you the answer. So there's your standard deviation, your mean, your variance, and then your sample standard deviation, your sample variance. So in this case, this was a sample. So we would be using the sample standard deviation sample down there. So the sample standard deviation is 2.17. Okay, much easier than doing it out by hand.
Wait, so standard deviation, how much are the outliers?
No, standard deviation is telling you spread. I'm going to explain what standard deviation is in 1 second. I want you to know how to calculate it, and then I'm going to explain what it actually means in terms of the actual curves. All right, so this is how you're going to do it. So on Monday, when you come for your test, you need something to get online. I don't care if it's your phone, your tablet, it's fine. Because this is how you're going to use calculated standard deviation and stuff. Okay? You're not going to do this out by hand. Okay. All right. I need... No. Hold on. I know what I'm looking for, and the book doesn't have it. This works. All right. So what standard deviation tells you is how spread the numbers are. So the bigger the standard deviation, the more spread out the information is. The smaller the standard deviation, the more compressed the information is. Okay?
So smaller is more compressed.
Smaller is more compressed. Or, as we were saying before, more consistent. Okay? So let's go back to those basketball players. So,
Larger is less.
That's the only one that's in belt shape.
believe it or not, all going to be bells. So we're not there yet when we start getting into the actual information and stuff. Once you get past about 30 pieces of data, they will typically fall into a nice bell curve. And the more data you have, the more consistent it is. So there will be a point where we have to figure out if it's a normal curve. If the data is all over the place, it's obviously not. But if it's a normally collected data, they will fall into that information, so we don't have to worry about that piece. All right. So to load up calculator.net and find me the standard deviation for these two basketball players. Or whatever calculator you want to use. And since these are all the games played, you can use this. You're going to use the population one, not the sample one. If you've done it correctly, this is what you should get. If you don't just write this down, actually do it, because I want to make sure you can do this before you leave.
I can't log on.
You shouldn't need to log on. Oh, you have no service. Log in the Wi-Fi. Service is horrible in this building, I will tell
I
you.
know, I don't know my ID number, so I have to look, I'm trying to look that up, but I can't even look that up.
Okay.
I think you got the second one. Just 16,
Maybe. That's possible. I could have typed the number in wrong. 2, 3. Oh, I did. I put 3 instead of 5. You're right. I did. I put 3 instead of 5. So 11.26. Okay.
Hey, Tony,
Yes.
when we go into that calculator.net, are we
You're looking
picking
for.
the scientific
Nope.
calculator?
That should be a statistics.
There's a search box somewhere too.
That's what.
Thank you.
You're welcome. Everybody else find it?
Mhm.
Or find something that works for them? Yes. What do you? Yeah. Oh, no, we're not going past that. 2 decimal places is fine. Typically, so if I remember my science class, it's normally go one more significant digit than what you have in your problem. I always go 2 places after the decimal place. So I hated significant digits. I always round it to 2 decimal places.
I got 12.589.
You're looking at the wrong one. It's the standard deviation.
Oh yeah, make sure you're using standard and not population, or the sample one.
Yeah.
So you got 11. You should have 11.26 for standard deviation. The sample one is 12.589. So because there is 2 different ones to do it, and we'll change your answer. Yeah, the population. This is population. No, because we have all the data, so this is technically population.
But anyway,
Yeah, so if it was a sample, you just click sample and it's going to give you that other. It'll be because remember the sample, we don't have all the data, so you're going to want a larger variance to be able to determine information. So that's why your sample standard deviation is a little bit bigger typically than your population standard deviation.
In the instance, it's like 12.58, you can round that up to 1 point.
Yeah, it'd be 12.59. Because it would be the 9 would tell the 8 to go up to 9. So in that case.
Aren't they have like population sample with this?
Because it doesn't know what you're using, what this is. So this could be a sample of those players. I could have said, this is a sample of 5 games from player A and sample of 5 games from player B. And then we would have used the sample one.
Oh, yeah.
I was telling you, these are the 5 games for each player. So we have all the information. So that's a population. So it really just depends on what the question's asking you and giving you, determining which one you're going to use. So we were talking about before, player A was more consistent, and that shows with the standard deviation. It's a smaller standard deviation. Okay, the ones that's really far out there, their standard deviation is quite large because their variance is quite large. So standard deviation gives us the ability to determine consistency. Okay? Yes. Oh, sorry. I didn't know if you had a question. That's okay. You both actually were doing the exact same thing. Like I wasn't sure if there was a question. So that's where we use standard deviation for. You are not going to have to sit there and do it out by hand, ever. And I will tell you right now, no statistician ever does it out by hand. We use Excel. Okay? You're not doing the stuff out by hand ever. So don't stress out about it and go, somebody's going to ask me to do it. They're not. Yes.
That's what you use as population.
That's population. Yeah, they're both population. No problem. All right. So now let's actually a couple little things about standard deviation. All right. Standard deviation is always positive. Standard deviation could be 0. That's if every single number is exactly the same. Okay? If all the numbers are exactly the same, the standard deviation is 0. Standard deviation is not resistant to outliers. If you have a lot of an outlier in your data, it will pull the standard deviation. And standard deviation is the same units as the actual data. So if we're talking about like feet or whatever else it is, standard deviation would be in terms of feet. All right, now how do we use standard deviation?
How would you say it using the same units? So like player A was 3.5, and you say
Points.
they make.
And these would be points. Those are the points.
It's like
It was 10 points.
3.5, 2 points. Or
No. No, that's it. The standard deviation is 3.52 points. You're going to see where that comes in a second. Because I'm actually going to use we're going to talk about the empirical rule, and I'm going to actually talk about what it means on either side in a second. All right. Probably the most important rule that you're going to see for standard deviation. Write this down as I get another thing copied over, or another thing found because I need the exact number. All right, so the empirical rule. As long as it's a bell curve, it's a standard or normal distribution, 68% of all the data will be within one standard deviation of the mean. 95% of the data will be within two standard deviations of the mean. And 99.7% of all the data will be within three standard deviations of the mean. Everybody got those three things down? Okay. I'll give you one more minute. I'll give you a minute. It's fine. All right. The height of adult men in America is normally distributed with a mean of 69.2 inches and a standard deviation of 2.66 inches. Okay. So that's what this is what this means. So here's our empirical rule. So the mean is 69.2. So that is the middle. Okay. That is our mean, median, and our mode. All right. The 2.66 inches is how much it's spread. So the standard deviations go both directions. So going this way, we're going to add 2.66 inches. Okay. So we're going to be at 71.86 inches. Does that make sense? Okay. The other direction, we're going to subtract 2.66. So, okay, somebody do that real quick for me. 66 point what? 0.54? 52? 54. Okay. So 68% of the people, or men, will be between 66.54 and 71.86 inches. That's what standard deviation means. Okay. So we can now determine, okay, that's the 68% of all men are going to be between those two numbers.
So basically, just like you take the curve and divide one side of it.
Mhm. The bell curve goes on forever.
Yeah, it's mostly.
Right. That's the 99.7 isn't 100%. You will never get to 100%. It just gets smaller and smaller as you go out. Past 3 standard deviations is extremely rare. It's 3 out of every 1,000 people, basically. So we do the same thing again for the next one. We add 2.66 and we subtract 2.66. So 95% will be between. I really should just keep my phone out and actually do it out. Okay. And what's the lower side? 63.18? 88. Okay. So 95% of all men are between 63.88 and 74.52. And if we do it one more time, 77.18. And the lower side? Okay. How tall is the door? 80 inches. Even going out 3 standard deviations, it's still lower than 80 inches. Okay. So that's what standard deviation. So you're asking like, what does that mean? That's what it means. So on average, when we're looking at the data, we can assume that this is the case for anybody. Okay. Does that make sense? Okay. What's the most famous case of where the bell curve is used? Huh? No. If any teacher ever tells you they grade on a bell curve, run away from their class immediately. No, because somebody is guaranteed to fail. A true bell curve, there's got to be one person getting an F and one person getting an A. The majority of the class gets a C. That's what the bell curve is. So if they tell you you're grading on a curve, run. A bell curve, run. Because odds are they don't know what they're talking about. Or they do, and it could be very bad. So the most common use for the bell curve is in IQ. So IQ scores, and the bell curve back. IQ scores is a standard, or the mean is 100. So for IQ, your mean is 100. Actually, I'm going to use the correct symbols so this way you can get used to seeing them. And your standard deviation is 15. So 100 is in the middle, and we add and subtract 15 from both sides. So you go 85 to 115, 70 to 130, and 55 to 145. That score right there is a score that represents a mental deficiency. If you're below 70 on the IQ score. Okay. So approximately 2.35% of people would fall into that situation. Okay. If I asked every single person in here to write down on a piece of paper what you think your IQ score was before I did this, everybody would be higher than you're supposed to be. Because inevitably everybody thinks they're way over in this area. But again, actually, above 130 is only 2.35%. Above 145, you're at 0.15% of the population has an IQ above 145. So you want to do a nice little experiment with your friends on Facebook or Instagram, whatever you're using, put a little poll out and ask what your friends think their IQ score is. Yeah, you're 1 out of 1,000 in your IQ score. Okay, so but this is where actually the bell curve really gets seen a lot of times is when you're talking about IQ. And if you take any of the IQ tests online, they're really, really bad IQ tests. Don't believe any of them. There actually is true IQ test, and it's a very long test that you have to take, and there's a lot of stuff that goes into it. It's not 10 questions that are going to give you your IQ at the end of a little thing, and it's not always about moving boxes around and stuff on the screen. So, but that's what the standard deviation means. Does that make sense? Okay. All right.
Yeah, the symbol for the one thing that might make me to remember is that
It looks like an M.
yeah, it actually is.
It's the Greek letter mu. Yeah.
It's like a really fancy view.
Yeah, they're Greek letters. It's the Greek letter for mu, which is M. So that is not that far out of the realm. All right. All right. I'll have you guys do one more of these. All right. So their average daily sales is going to be 45,000 and a standard deviation of 750. Huh? 45. Oh, I did say 45,000, 4,500. How many days out of the year would you expect their sales to be below $2,250?
Is it 0.3%?
Huh?
Is it gonna be 0.3% fish?
No. Hold on. I got to go back one screen because I need my bell curve. All right. I'm going to get my bell curve again.
Below it or at the? same?
Below it. All right. So first step, what you have to figure out? We're going down, right?
Yeah.
So we're not going up. So we're going to keep subtracting. So 4,500 minus 750. Minus 750. That's 3,750, right? 4,500 minus 750 is 3,750. Minus, yeah, minus 750 is 3,000. Minus 750 is the 2,250. Okay, so it's 3 standard deviations, right?
Oh, I thought you said below 2.
Right,
That's
right. So let's look at our bell curve, right? So 1 standard deviation, 2 standard deviations, 3 standard deviations. So 2,250 is here, correct? So we're looking at that number, that amount right over here, correct? Okay. So this is 99.7%, right? So how much is over in this spot here?
Like 0.15.
Yes. It's 0.15%.
So it's like 56 days of the year.
Oh, yeah, 0.15.
Almost. All right. So step 1, everybody understand where I got the 3 standard deviations? Okay. Everybody understand where I got the 99.7? Okay. Because remember, 3 standard deviations for the empirical rule is 99.7. Where did I get the 0.15? What's left over is 0.3, right?
That's like,
But that's on both sides. So it's 0.15 on this side and 0.15 on this side.
just the remaining.
All right, so hold on, let me go back to my curve here. Remember I said up here, I said only 0.15% is above that. because down here, it's also 0.15%. That's where you get the 0.3 left over from the 99.7.
Oh,
So those percentages never change.
No, those percent, that's the empirical rule. So remember, we're back to this. That's the empirical rule. Are those the exact numbers? No, they're slightly different, but they're really close. And if you wanted the exact numbers, you have to take calculus. I make my calculus class figure out the exact numbers.
so outside of the third standard deviation would be like
On either side,
on either side.
correct.
The exact numbers will be different for each set of data.
Well, no, the 66, 68, 95, and 99.7 will always be the same.
Yeah, but like you said,
The actual, like the amount, the actual numbers, like in this case, it was 2.66, and those numbers, those change. In this case, it was 4,500 was the middle, and we were subtracting 750. Those numbers change. The percentages never change.
The rule, we could pretty much say 0.15% of the time, it's 4 deviations or more.
It's more than 3 deviations. Yes, more than 3 deviations away. All right, so now, what's 0.15% of 365 days? It's 0.547. It's half a day. Okay, because it's 0.15%, which is 0.0015.
Oh.
So it's literally 0.55 days. So you would expect them possibly to have one day under $2,250.
What did you say?
Remember, move to decimal places. Percentages move it by 2 decimal places.
I know the bottom.
I multiplied 0.0015 times 365. So the possibility is that there's one day that they'd have under $2,250 over the course of the year. Okay. There was a couple reasons I did this problem. One, I wanted to see how many people messed up their percentages, which is that's a normal occurrence. So don't ever think about like I would rather you make those mistakes now and in class so I can explain them and tell you than doing it on a test. So when I do think I will do this stuff a lot. Like I will put a thing out there that literally is designed to find those little mistakes that people make. So you make them now. Okay. So don't feel bad. There's a reason for them all. All right. And this one was a little more complicated than the just calculating it out. There was a bunch of little steps to it. Okay. And then you go the other direction, it'd be the same thing. So if you added 750 3 times to that, you'd expect to probably have one day above that amount. Okay. So it should balance out to about $4,500 a day over the course of a year. Okay. All right. Next thing. So the bell curve allows us to look at all the data and breaks it down into standard deviations. There's other ways that we can look at variance, however. This is one of the ways. And it's the most popular way. The next thing we're going to look at is known as percentiles. And I'm actually going to give you the little flow chart. All right. So to find percentiles. So the median is the 50th percentile. Okay? Because it is the middle number. Okay? So percentiles is telling you what percent that number is above other numbers. All right. So if you remember taking the SATs and you remember getting your score sheet back for the SATs, on that score sheet, it told you what percentile you were in. That basically tells you what percentage of people you scored higher than. Okay. So if you were in the 70th percentile, you scored higher than 70% of the people that took that test. Okay. That's what percentile means. All right. So it's the same thing as median, where you have all the numbers put in order and you're trying to find out where you are in that list. Okay. To do that, this is the steps to do that. The formula is n, which is the number of values in your list, times p over 100. So whatever percentile you're looking for, divided by 100. So if, for example, I had 500 people, so n is 500, and I'm looking for the 30th percentile. I would do 500 times 30 divided by 100.
What's L?
L is the value. That's the value. That's the next step. So in this case, it's 150. For the case that I just did.
L1.
Yeah, location. Okay. Now, there's two steps. So in my case, L was 150. If L is an integer, which means a whole number, like an actual number, no decimal, you're going to average the two values. So we're going to take 150 and the 151st number, add them and divide by 2. Okay, so it's whatever number those are. So the 150th number and the 151st number, add them and divide by 2. So whatever number you get, if it's an integer, it's that number and the next number. And that's your percentile. If it's a decimal, you just round up and that's your value. Okay. So say it came out to be 150.5. I would just take the 151st number. So if it's a decimal, you always round up and take that number. All right, now let's do it with actual numbers. And I'm giving them to you in order, so you don't have to put them in order. All right, let's find the 10th percentile. There are 40 numbers here, so n is 40. There's 40 numbers. So we would do 40 times 10 divided by 100. Which is 4. That makes sense?
So the fourth number is because we're ordered 10% value.
No. This is, yes. I counted up how many numbers there was. I knew there was 40 of them because I pulled it. But yeah, there's 40 numbers. It's an integer, right? So integer says I average it with the next one up. So I'm going to look at the fourth number and the fifth number.
Oh, those are in order.
Yes, they're already in order. I gave you the ordered list, so we didn't have to put them in order. So we're looking at the fourth and the fifth number. So the 10th percentile is 27 plus 29 divided by 2, which is 28. So the 10th percentile is 28. Yes. Because you're always rounding, like, because you can't have an actual, like, the exact spot when you're looking at percentages. So if it comes out, it's kind of like what we did with the widths. Remember when we came out, it didn't work. So you need to round up. That if it's a decimal, you're rounding up. Since it's not a decimal, you need to calculate somewhere in between those two. So if it's an integer, if it's a whole number with no decimal, you're always going to do that one and the one next to it and find the average. Okay. All right. Your turn. Find me the 88th percentile.
Hey, you round.
Always round up.
Okay.
Yes. Rule says if it's not an integer, you round up. So this one comes out to be 35.2. So I'm using the 36th number. Which is 73. Okay. All right. Hold on. I need this. All right. Everybody got those two? Does it make sense? Right. The decimal, you always round up. Doesn't matter what the decimal is. I know it's weird. No, you always round up. All right. How many people have seen this before?
I remember having to do them in like psychology.
This is a box and whisker plot. All right. This is a box and whisker plot. So they call it a box plot. I always called it a box and whisker plot because it looks like it has whiskers like a cat. It is also the 5-number summary. So if you're looking at a set of data, you can organize into 5 numbers. Okay. Those 5 numbers are the min, Q1, the median, Q3, and the max. Min and max are pretty obvious. Q1 is the 25th percentile. Median is 50th. And Q3 is 75. So all a box and whisker plot does is break it into quartiles. Okay, 4 parts with an equal amount of data in each part. It gives us a visualization of how spread the data is. Okay, this one, the boxes are pretty similar. Okay, and they're pretty much in the middle. But if they were skewed to one side or skewed to the other side, we can start getting that understanding of that, the way the data looks without having to look at all of the data. So in the problem in this problem here, if we look, the lowest test score is 18, the highest test score is 82. So that's where the 18 and the 82 came from. Okay. The other 3 we can calculate just by finding our percentiles. So if we did L is 40 times 25 over 100, you get 10. So we're looking at the 10th and 11th numbers, which is 41 and 43. So that's where that 42 came from. Okay. The 50th would be your 54 and 54. So your median is 54. Your 75th would be 64 and 66 because it's the 30th number, 30th and 31st. So we have the 65 there. So you don't have to do like all this counting and everything else because we know how to find percentiles. You can find those 5 numbers quite easily. And then all it is putting them on a number line. Yep. It's always that. It's the quartiles. It's the 4 quarters. 25, 50, 75, and the 100, and then 0 is min. Now, the last thing we're going to talk about today is, because we were asked, what about an outlier? What's an outlier mean? This is how we find out our outliers. So this box in the middle here, that's known as my interquartile range, IQR. So it's the range from the 25th to the 75th percentile. So it's that box. So my interquartile range is 65 minus 42, which in this case is 23. Yeah. The beginning and the end of the box. So it's the 25th percentile and the 75th percentile, basically. And so, yes. Yep. That's your interquartile range. So the interquartile is between the 2 quarters, so Q1 and Q3.
So what the color?
They just use those colors. It doesn't matter.
Separate the middle.
Yeah. Yeah. Most boxes you're going to see just don't have any colors there. It's just open with a line in the middle of it. So your interquartile range is 23. Okay.
And that'll always be the first and the last.
It's always the first and last in the box. That's why it's the 42 and 65. It's not the min and the max. So it's Q1 and Q3. Did I totally confuse you? So first and last, I always think of min and max. So it's not those 2 numbers. It's the numbers up here. It's the 42 and the 65. Okay, yes or no? Okay. Because outlier really matters with this. So your outlier is 1.5 times your interquartile range. So what's 1.5 times 223? $34.4? 34.5. Okay. Oh, that's right. All right. So your outliers are going to be those added to your Q1 and Q3, or subtracted from your Q1 and added to your Q3. The outlier is 1.5 times whatever your interquartile range is. It's always 1.5 times whatever your interquartile range is. That's why it's so important to find that interquartile range. So we're going to take 65 and we're going to add 34.5. And we get 99.5. And then we're going to take 42 and we're going to subtract 34.5. And we get 7.5. So if we have it, so you're adding it to your Q1 and Q3, or adding it from the Q3 and subtracting it from the Q1.
The Q1 and Q3 already used to decide how big the box is.
Those are any numbers outside of those would be considered outliers.
Anything outside Q1. Or
Yes.
anything that far out.
Anything that far out would be considered an outlier.
Okay, so there's things that are like not outliers, but are not outside the box. No, anything outside the box.
So no, so yes, they'd always be outside the box. They could never be inside the box. So basically, if the kid scored 100 on their next test, or somebody scored 100 on the test, that would be considered an outlier based on this information. Okay, or if a kid got a 0 on the test, that would be considered an outlier based on this information. Would be considered outliers.
34.5. So it's less than 42, but it's not like if it was in between those, it's still be an outlier.
Okay, 34.5 isn't the outlier. You're adding 34.5 to your Q3, which is how we got the 99.5.
Okay.
Any number higher than 99.5 would be considered an outlier. We do the opposite to the other end. So you take the 42 and you subtract 34.5. Anything lower than 7.5 would be considered an outlier.
Yeah.
Okay. That's how we determine an outlier. It has to be 1.5 times more than the interquartile range.
Okay, so then there are ones not in the interquartile range, but are.
Yeah, they're between 18 and 82. Yeah. And actually, if you look, the way this table was set up, there's 10 numbers between 18 and 42. Those 10 tests were in that first quarter. So this is in that first quarter. This section right here. This is in your interquartile range.
So which ones are outliers?
In this case, we have no outliers because all the numbers are between 18 and 82. So nothing's less than 7.5 and nothing's greater than 99.5. So we don't have any outliers in this situation. Okay. If you did, then that's where you have to start looking at. It's like, okay, honestly, a lot of times your outliers, you would not have to go through and do all this work out. It's going to be so far out there. You go like, that's obviously an outlier. The problem comes into is if your numbers are really spread out your interquartile range could be quite large. So you might have a number that's looks like an outlier, but technically isn't. Okay. So that's where we'd have to do some calculations. But if the numbers are all pretty relatively close together, you should be able to tell pretty quickly if it's an outlier or not. So this will just confirm that piece. All right. And what you do, let me see if I can, yeah, this is, so they added a couple test scores just to show you what the outliers look like. So when you label your box and whisker plot, if you have an outlier, it's a little dot. And your min and max stays, does not go down to the outliers. So your min and maxes are where they are without the outliers put in. So in this case, we had an outlier below and above, so they put little dots to represent the outliers. Huh?
I said that poor kid.
I know, right? What about the nice kid that got 110?
Oh, so there's outliers.
Yeah.
There's outliers, but like they're higher. So in this case,
Your outliers will always be outside
Yeah.
the box and whisker because they're
the
outliers.
whiskers mark where
The whiskers would mark where the min and max is, excluding any outliers.
okay, yeah. So you decide what the min and max is using that.
Yeah. Once you get your box, basically your interquartile range to 25, you can figure that part out, and then you can determine if your min and max is the lowest and highest number, or do I need to eliminate an outlier to make my min and max. Okay. And I think that's all we're going to do tonight. Oh, actually, I got one other thing I have to do. Sorry, guys. Just because I know this shows up on the test. So. Actually, hold on. Give me 1 second. I want to see first. Because if it's not, doesn't show up on the test, I won't put it aside. I'll do it next week. All right. You do not. Okay. All right. So we won't do that today. If you get anything on your homework about z-scores, I didn't cover those. I'll cover them next when we actually start talking about the standard deviation again. So, all right. Your test is on Monday. There is a review test online in Hawks for chapters 1 through 4. If you do that, that's literally what your test is going to look like. It's just with different numbers.
So
See you Monday.
the lesson's gonna be
I will have them up there tomorrow morning. It's the first thing I do in the morning when I get up. I post the videos. They should have been up there from